This video is about how I made peace with square root of minus 1, or in other words, imaginary and complex numbers. Well, 90% peace I would say. The main why questions that I had were, why focus on square root of minus 1 that cannot even exist in reality? And why make it a separate perpendicular axis? Why consider imaginary exponent and consequently e raised power an imaginary power theta that can equate cos theta plus j sine theta? If you're already clear about these whys, you can skip this video. If not, carry on. It made sense to me when in early years we were taught about numbers being used to measure quantities like temperature or length. It also made sense to use negative numbers to signify direction. For example, considering plus 6 centimeters as 6 centimeters towards right and minus 6 centimeters as 6 centimeters towards left, and resultant conceptual model of real numbers line on which many real-life quantities could be mapped. Then came square root of minus 1, often called iota, that is small I or small j. It was obvious that there can't be any real number whose square is minus 1, so square root of minus 1 should not exist. But we were told to be not too fast and hold on and think of it as a separate axis. And if we do that, we can certainly carry on with operations like addition and multiplication, though in a slightly different way than real numbers. Firstly, the numbers would exist in a resultant 2D plane. That is, 3 plus 1j would mean 3 units of real axis and 1 unit of imaginary axis. If we want to add two numbers, we can add real part with real part and imaginary part with imaginary part. Visually, we can do it using head-to-tail rule. It's similar to adding two vectors. Multiplication was a bit different. We can algebraically multiply, and wherever we encounter j squared, it will be equal to minus 1, which is obvious as j is square root of minus 1, so its square will be equal to minus 1. Visually, it's equivalent to finding the angle that any of the arrows makes with the real axis and rotating second arrow with that angle, and then scaling the second arrow's length by the factor of first arrow's length. Due to this, at times we feel more comfortable in writing complex numbers in amplitude angle form, where a is the length of arrow, also called amplitude, and theta is the angle it makes with the x-axis. So the product can be taken by multiplying amplitudes and adding the thetas. Multiplication is different from vector multiplication. In vectors, there are two kinds of multiplication. The dot product produces a scalar, and cross product takes you out of the input plane into a perpendicular plane. But in complex numbers, we don't end up in a scalar, we end up with another complex number, which is similar to a vector, and we also remain on the same plane. But then another interesting yet puzzling form was introduced to represent complex numbers, that is e raised to power j theta. Now theta being an exponent naturally means that in multiplication angles will be added while amplitudes will be multiplied, just like amplitude angle form. In that sense, it made somewhat sense. But what does it even mean to have an imaginary exponent? Normally, when we say 3 raised to power 4, it means multiplying 3 4 times. But what does it mean to multiply 3 an imaginary number of times? But from figure, we see that with j in exponent, in this world with imaginary plane, it means rotating at an angle in exponent. Even if we accept that ye, that is a specific value 2.718281 and so on, what does this value has to do anything with rotations and trigonometry? But if we accept that and then consider the special case of amplitude equal to 1, we can see that e raised to power j theta is equal to cosine of theta plus j sine of theta. Because since the hypotenuse is 1, so base should be equal to cosine of theta and perpendicular should be equal to sine of theta. Changing the amplitudes in the circle will increase its radius, and by changing theta, we get this rotating arrow that is at the heart of so many fields, from signal processing and digital communications to quantum mechanics. At times, we prefer to see theta as a separate axis, and then this arrowhead traverses a spring-like shape. If we don't ask too many questions, this pretty much covers the how kind of questions, but does not answer the why kind of questions. And based on this understanding, most engineering courses can be easily covered. But making square root of -1 as a separate axis felt like a bit of cheating to me. Cheating that helps solve a lot of problems, but still looked a bit of cheating. Many authors try to put it as a bad naming convention to call them imaginary numbers. But to me it always felt right because no real number can be squared to get -1. Now comes the making peace part. I primarily had two main whys. Why focus on square root of -1 that cannot even exist in reality, and why consider it as a separate perpendicular axis. And secondly, why consider imaginary exponent, and how can e raised power imaginary power can be equal to cosine of that power plus j sine of that power. Let's focus on the first one. Let's revisit real number lines again. Negative side was introduced to signify direction, that is right or left. Positive towards right, negative towards left. But we also use it for direction reversal. That is, multiplying a positive number by -1 reverses its direction, and multiplying a negative number by -1 also reverses its direction. And this behavior of reversing the direction is unique to -1. It doesn't apply to +1. Multiplying a positive number with a positive number doesn't change its direction. Neither does multiplying a negative number with a positive one changes its direction. This direction flip is rotation by 180 degrees. If we keep multiplying by -1, we keep rotating by 180 degrees. So this relation of multiplication and rotation actually comes from defining multiplying by -1 as a direction flip. What if we want to rotate by 90 degrees instead? We need something that done twice would result in 180 degrees. And since 180 degree rotation is multiplication by -1, it's obvious that the thing multiplied twice to get 180 degree rotation should be square root of -1. So now it makes perfect sense to consider multiplication by square root of -1 as rotation by 90 degrees. It also answers our first why question. From this perspective, we can consider square root of -1 an operator that rotates by 90 degrees. For some, this explanation is good enough to say that the term imaginary is a bad naming convention. But to me, non-existence of any real value as a square root of -1 still remains a fact. So I think the name imaginary is good enough. Now comes the second part. Why consider imaginary exponent? Before that, I would like to take a complete detour. What does graph of x raised power n looks like? If n is 1, it's a straight line. If n is 2, that is x squared, it's a parabola. It grows much faster than a line. And since multiplying a negative number by itself results in a positive number, so it's symmetric around y-axis. This is also true for any even power of x. If n is 3, that is x cubed, it grows even faster because a number is multiplied 3 times. But multiplying a negative number odd number of times keeps it negative. So for odd powers, the graph is not symmetric around y-axis. But left side is actually the right side flipped around y-axis and then flipped around x-axis. If we zoom in, we see another thing. For x is equal to 1, x raised to any power is 1. So all these curves pass through 1, 1. For values less than 1, multiplying multiple times results in a smaller number, while for greater than 1, with each increasing power growth is much faster. On the left side, even powers pass through -1, 1, and odd powers pass through the coordinate -1, -1. Now, if we expand each graph by dividing x raised to power n by a constant n factorial, we get an interesting pattern of almost equidistant curves, especially in the range from -1 to 1. Keep in mind this pattern of x raised to power n over n factorial curves while we explore some more patterns. Now let's focus on even powers only. And let's also consider the case of x raised to power 0 over 0 factorial, that is y is equal to 1 as well. Now if we add these curves, they will grow rapidly on both sides of y-axis. But if I flip some of these curves, it will make a very interesting pattern, as if we are weaving an interesting graph. Let me show. But before that, two things. I will show the curves in blue and their sum in black. And for simplicity, instead of calling x raised to power n over n factorial every time, I'll call it curve n. For example, curve 0 means x raised to power 0 over 0 factorial. So at start, sum is 0. Let's start with curve 0, which is basically y is equal to 1. So the sum moves there. Now let's flip over curve 2 by negating it and add to sum. The curve moves up to 1. Now let's add curve 4. Then let's flip curve 6 and add. And then add curve 8. Flip curve 10 and add. Then add curve 12. Flip and add curve 14. Add curve 16. Flip and add curve 18. Now this sum is taking a familiar shape, right? It is approximating cos of x pretty well. See how good it's fitting. Let's see a zoomed out variant with some more terms. Look at that. Isn't it amazing? These even powers of x raised to power n over n factorial terms weaving a pattern to form cos of x. We can say that adding infinite terms will equate this series sum to cos of x. Do we see a similar pattern with odd power terms too? Here is a graph of odd powers. Let's do the same thing. Sum is 0 at start. We add curve 1, then flip curve 3 and add curve 5, flip curve 7 and add curve 9, flip curve 11 and add curve 13, flip curve 15 and add curve 17. Well, this sum is taking a familiar shape too. It's approximating sine of x. Look how good it's approximating. Let's zoom out and add a few more terms. Look at that. Wow. I can keep looking at it again and again to form this weaving kind of pattern. And if we add infinite terms, this series should approximate sine of x. Instead of even and odd terms, let's focus back on all x raised to power n over n factorial curves. If we start adding these curves, on the right side, values should add quickly to grow very fast, while on the left side, they might somewhat cancel each other out because we have both negative and positive numbers. Let's try this. The sum is 0 at start, add curve 0, curve 1, curve 2, curve 3. Let's keep going. This curve seems familiar too. It's e raised to power x. See how good it is approximating. As e raised to power x grows pretty quickly, so it would be better to see a bigger span. Let's extend y-axis to 20,000 and see how good it converges. The red line is e raised to power x, and in around 10 terms, we can see how good it approximates even for the larger values. If we add infinite such terms, the series should converge to e raised power x. By now we have seen that e raised power x can be represented by constituent x raised power n over n factorial terms. Uh, Even power terms of x raised power n over n factorial can constitute cos of x, while odd terms can constitute sine of x. But in cos and sine, we need alternating signs. If we had a way to alternate signs between negative and positive after every two values, let's denote that way by a box. Then we could apply it and get e raised power box x is equal to cos x plus sin x. But we don't exactly have that. But this series has given us something close to this. This series gives us an alternate way to look at exponents, a way in which we can take an imaginary exponent as well, which will take us close to what we want. E raised power jx would mean that we will replace x with j of x on both sides. So on the right side of equation, each term we can replace x with j of x. In each term, then we can separate j raised power n from x raised power n. The first one, that is j raised power 0, is on real axis. J raised power 1, that is j, takes us to imaginary axis. J squared is minus 1, which takes us to negative real axis. J cube is equal to minus j, and it will take us to negative imaginary axis. J to the fourth is again j squared times j squared, that is plus 1, which will take us to real axis. J5 is j raised power 4 times j, that means a single j, which will take us to again imaginary axis, and this pattern keeps repeating. Now we are getting two positive signs and two negative signs that we actually wanted, but we have an extra j with some of the terms. We can see that even terms are equal to cos of x, while in odd terms we have j, which we can take common, and this will equate it to j sine of x. So finally we reach the magical equation e raised power jx is equal to cos of x plus j sine of x. But this is not a simple y is equal to f of x kind of equation. We have an x-axis, but our function e raised power j of x can result in complex values. So we need a real and imaginary axis to represent that. At x is equal to 0, sine of x is 0, so f of x is 1. At x is equal to pi by 2, cos of x is 0, so f of x is j. At pi we get minus 1. If we go pi by 2 further, we get minus j. At 2 pi we get back to 1. And this pattern continues. If we fill in the values in between, the curve is an interesting spring-like curve around x-axis. Its projection on real axis is cos of x, and on imaginary axis is sine of x. And those two real and imaginary components add up to form this helix. Well, as Feynman has explained that in the end there is no end to y questions. You can ask that why is x raised power n over n factorial anyway related to exponentials and trigonometry? Well, I didn't want to throw Taylor series directly to explain this, but this comes from Taylor series. Grant's video on Taylor series is an excellent source for this, and I'll put a link in the description, but I'll explain it in another way. E raised power x, sin x, and cos x are special in a sense that they have very nice derivative properties. E raised power x is a function whose derivative is also e raised power x. So you can take as many derivatives as you want. Similarly, derivative of sin x is cos x, and derivative of cos x is minus sin x. So repeated derivatives takes us back to sine of x. So in both cases, we ended up from where we started. So that's a very nice property of derivatives here. So now look at the derivative of x raised to power n. We know that it's n x raised to power n minus 1. If we divide both sides by n factorial, as we can see that n factorial can also be written as n into n minus 1 factorial, so n cancels out. So well, this basically is the previous term in the series. So if we take derivative of whole series, the first term is a constant that goes away, but in the very next term we get derivative as a previous term. So since this is an infinite series, we get the same series back. So well, we found a series whose derivative is the same as the original series. So no wonder it equates with e raised to power x. I will leave you guys to derive what if we take even or odd terms and alternate signs, and then take derivative of the series. So I think you can guess what you would get. In the end, I would like to refer a few links. The first link is by my friend Qasim. He has written a very nice article on the same topic, and he starts from more basic stuff and goes to more advanced stuff in the end. The second is a tutorial by Rick Lyons, and it's an excellent tutorial, really excellent with some very good visuals, and especially for people who are interested in digital signal processing and digital communication. It covers quadrature signals and filtering and how to visualize them in 3D. It's a great link. The third link is from Welch Labs. It's imaginary numbers are real. Maybe you might have already seen this, but this playlist is awesome. I binge watched it. He has put great effort behind it. So it covers basically mathematics of it. It doesn't go to signal processing side, but it's a good link. And last is Grant's video on Taylor series, which is not exactly on this topic, but Taylor series is the general concept behind this x raised to power n over n factorial thing that we were using. It's a more general concept. You can actually approximate any curve using Taylor series if the series converges. So I would recommend all these links.